Okay, so today's lecture is going to be, please mute, Raish. Yeah, so today's lecture is going to be on cleaning up groundwater contamination. Now, up to the last lecture, we discussed different aspects of groundwater quality and how the contaminant travels in groundwater. So today we'll take it to the logical next step, which is to discuss how to clean up groundwater contamination once it happens. Now, what I'm going to try to do is um, give a brief overview of what the groundwater contamination problem is specifically in India, uh, and then we will talk about some of the uh, approaches that have been used around the world to clean up groundwater contamination, and then we'll get into a little bit of specifics about specific approaches that can be used. Okay, now the objective behind this is to hopefully motivate some of you to look at this as a serious problem. I shared one of the podcasts, I think maybe a couple of weeks back, which related to nitrate contamination in groundwater. And then at the beginning of the semester, I shared one more report, a newspaper article linking the groundwater contamination issues in India. So this is going to build on that and probably give a little bit more specific details on how to clean up this groundwater contamination. Okay, so that's going to be the objective of this particular lecture. Okay, I'm not trying to get you to memorize the details of whatever is going to be presented. So don't worry about it. The objective is merely to raise awareness about the issue. Okay, all right. So to begin with, we will talk briefly about the scale of the groundwater contamination problem in India. Okay, so all whatever data I'm going to present now is mostly coming from government sources. Okay, so whatever data is available with the Central Pollution Control Board, that is what I'm going to be showing here. Okay, so I have picked um, some well-known contaminants about which we have collected data around the country, and that is going to be presented. So on the left, you have a map showing fluoride contamination. And the dots that are shown, those are the locations where the fluoride contamination has been found greater than 1.5 milligrams per liter, which is the safe limit. Anything less than 1.5 mg per liter is not considered an issue. And then 1.5 and above is said to be a problem, right? So you can see that there is widespread fluoride contamination, and this is mostly from naturally occurring fluoride in the groundwater. Okay, so it's a mix of some issues are because of naturally occurring substances. Some might be because of both naturally and uh, human intervention. So it's a mix of the two, but in any case, the problem has to be solved, right? Okay. So you will notice that there's a lot of fluoride contamination in Rajasthan and quite a bit in Andhra Pradesh and Telangana and southern Tamil Nadu and so on. So it is pretty widespread, and the presence of fluoride in water, which if you drink beyond a certain quantity, then there's a problem called fluorosis, which affects the teeth and the bones and so on. And it's a serious issue, especially for young children. So excess fluoride contamination is a major issue. Okay, and people are trying to, figure out ways to solve it. The one in the middle, now that is another serious issue. That is showing nitrate concentration of greater than 45 mg per liter, and you can see that it is present pretty much across the country. Okay, now you might wonder, why is nitrate contamination? I mean, fluoride, for example, you see there are some hotspots, Rajasthan, and then Telangana, Andhra Pradesh, a little bit of Karnataka, and then Tamil Nadu. But there are other states, for example, UP does not seem to have too much of fluoride. Maharashtra only has a little bit, and so on, right? But nitrate seems to be present almost everywhere. Any idea why it's so widespread? Any thoughts? Anybody would like to volunteer a guess? Yash, Deepshika, you're the only ones I can see. No? Okay. So nitrate contamination predominantly comes from fertilizer application, right? And since agriculture is widespread across the country, naturally, nitrate contamination is also fairly widespread all over the country. Okay, so that's a human impact. Okay, then the one on the right there you see chloride contamination, and the light blue color that you see, that is chloride contamination less than 250 mg per liter, which is a safe limit. And so that's everywhere all across the country. Mostly it's below the safe limit, but wherever it's yellow, it's between 250 and 1000 mg per liter, and the pink color is more than 1000 mg per liter, which means the water is very uh, high in chloride concentration, and that can have major issues. Now, you'll be surprised to see that it's not only the coastal areas which are showing these greater chloride concentrations. You also see a lot of chloride in Rajasthan. Okay, now that is partly due to usually what happens is when you have a desert, um, uh, it's also typically the part of the world where you will find oil reserves are present in Rajasthan to a certain extent, and perhaps because of that, the oil industry, which extracts oil from these deep wells, uses a lot of brine, which is basically highly concentrated salt solution, uses brine in most of its processes. So that might be one of the reasons why you see very high concentrations of chloride in Rajasthan. It could also be that there is some naturally occurring brine in the deeper aquifers. I'm not aware of the geology of Rajasthan and the specific reasons for that. So there could be multiple factors, but one definite factor is the oil and gas industry, which is present in Rajasthan, in certain parts of Rajasthan. So that might explain. And of course, you can also see a little bit of in Gujarat. Jamnagar Petroleum Refinery is there, and so on and so forth. So that could be possible reasons. Uh, in addition to the fact that that's where the desert part of India is. Okay, so that's chloride. Moving on. Then we have iron concentrations greater than 1 ppm is being displayed here. And again, you see that iron is not present in certain parts, but there are other regions where you have a high concentration of very high values of iron. And seems like the Indo-Gangetic Plain, so which goes all through UP, Bihar, little bit of Jharkhand and West Bengal. You seem to have these very high concentrations of uh, iron. Okay, and so that again might be something to do with the nature of the geologic sediments and so on, which might explain why the Indo-Gangetic Plain seems to have the Gangetic Plain specifically seems to have this high concentration of iron. The next plot, very interesting again, is arsenic. Okay, now arsenic contamination is something that is again, it seems to be observed in the Gangetic Plain, right? You see UP, Bihar, and then West Bengal. It's seen. Bangladesh is not shown here, but Bangladesh is well known around the world as a place where there is significant arsenic contamination in the groundwater in Bangladesh. Now, what people say is that this is due to the specific geology in this region, where you have very fine grained sediments because it's a nice alluvial aquifer and so on. So the geology is conducive for the mobilization of arsenic, right? So arsenic is a heavy metal, and it's extremely toxic. Okay, so the present arsenic poisoning can actually kill people. Okay, so and it so happens that in this particular belt of the Gangetic Plain, you have the specific conditions that makes the occurrence of or the mobilization of arsenic possible because of the oxidation or reduction, whatever it is. The chemistry part of it, I'm not very clear on exactly what happens, But in any case, you can read up. There's lots of articles about arsenic contamination in the Gangetic Plain and in Bangladesh, and that might be able to shed some light on the geologic factors and the chemistry that plays a role in mobilization of arsenic. The next one, the uranium contamination. Now, this is a serious one. Okay, uranium contamination mostly is coming from not from human impacts. It is mostly coming from naturally occurring uranium in the groundwater. Okay, and then you can see there are quite a few points in southern Andhra Pradesh, which is where we are. I mean, our campuses and so on. And I don't know if I told you guys, 5-6 years ago, 2019, there was a major uranium contamination issue in a village in um, uh, Kadapa district, and 3 or 4 of us, Shihab, Suresh, and I, we had gone to that location as part of a committee to look at the possible causes and what kind of things could be done to resolve the problem and so on. Anyway, so we submitted a report along with, there were experts from around Andhra Pradesh, from the Pollution Control Board and so on, and we visited the locations and we looked at it. So uranium contamination is there in southern Andhra Pradesh because there is naturally occurring uranium in that part. And then again in the Punjab, Haryana, that belt again seems to have a lot of uranium contamination. Now, it is not known whether this particular contaminant has got anything to do with um, over extraction of groundwater, because when groundwater over extraction happens, then the conditions in the aquifer start changing, and that can cause some kind of a chemical reaction to precipitate out the uranium which is naturally occurring. So if the groundwater levels are very high, then for some reason the chemistry of it is not very clear to me. The uranium remains either in solution or it remains in the rock and does not get precipitated out. But when the water levels start to drop, presumably uranium starts to uh, get mobilized and precipitated out or dissolved out at greater rates than if it were at if the water level was not going down. Okay, so it has a complicated role, right? So water use is also playing a role in water quantity. I mean water quality, right? So the amount of water that you extract plays a role in determining the water quality. Now, this is a very unusual, peculiar feature which is specifically seen in the case of groundwater, where uh, the more the groundwater quantity, the groundwater quality seems to be okay as well. As soon as the groundwater quantity starts to decline, the quality also starts to decline due to various factors, including the chemistry and the geology of the particular location. Okay, so anyway, all right. So basically, what I'm trying to tell you is that these different contaminants, I have only spoken about these few materials like nitrate, chloride, fluoride, iron, arsenic, and so on. Right? We have not spoken about industrial contamination, which could have petrochemicals or industrial solvents like tetrachloroethylene and benzene, and so many other chemicals are used in the industry, and it is well known that a lot of these industrial units do not dispose of their chemicals in a very safe manner. So there have been reports of high concentrations of very volatile organic compounds being found in the groundwater, right? So then naturally this raises the question of if this is the scale of the problem, right? It's not a problem that's localized in one part of the country or something that is happening only in a particular region, right? So you have wherever there are industrial clusters, right? Typically Punjab, Haryana, that region, uh, there's a lot of industrial activity. Then in Maharashtra, Andhra, Tamil Nadu, and so on, wherever there's a lot of industries being set up, right? There is a significant amount of contamination happening due to improper practices, right? Now, for example, if you go to Renigunta, right, there is a place in Renigunta called Autonagar. Okay, now this auto nagar is where if you have any complaint with your car or two-wheeler or any vehicles, you will take it there for getting it repaired. Right now, they use all kinds of chemicals to they change the oil in the car. They might change the transmission fluid. They might change the uh, whatever fluids, engine fluid, and so on and so forth. So many liquids are used in these modern cars, right? Now, what do they do with the old engine oil? They remove the old engine oil and then pour the fresh engine oil into the car. Now, what do they do with the old engine oil? They're supposed to keep it in a safe container and then dispose it off safely. But to what extent does it happen? Even if you visit that place, you will notice that there's a lot of oil leaking on the ground. And when there's a rainfall event, then that water will carry that oil into the ground. And so, therefore, there's going to be contamination happening, not just at a particular point, but it just spreads over a large area because there are so many sources. It's not limited to only one particular point. That's what is called non-point source pollution, right? It's not a point source. It's distributed all over the place. Okay. Anyway, so the scale of the problem is massive, right? Which means that we need to have some way to address this problem. Okay. All right. So, like I said, so we have all of these different industrial clusters around the country: Ludhiana, Tirupur, Vellore, Ambur, etc. And they're using all of these different compounds. I've just listed a few of them. Heavy metals are also present. And then we, of course, have the other problem of saltwater intrusion, uh, because we have aquifers all along the coastline of India, which is almost 7,000 kilometers long. And then there's the brackish water in Rajasthan. We already saw that. So all of these combined, when you look at the issue overall, it seems like a really massive problem, right? It's not that only one location is contaminated. Majority of the water present across the country is contaminated, and we already have evidence for that, right? So you might have seen recent news about the Yamuna in Delhi, really polluted, right? Because um, uh, the sewage water, the untreated sewage, is let into the river, and then that contaminates the river, and then the river is in contact with the aquifer. So there might be some exchange of contaminants happening between the aquifer and the stream, right? So basically, it is a problem of epic scale, right? So we need some solutions for this, right? So anyway, so yeah, I mean, I've spoken about all this. Now the challenge um, with groundwater contamination is that it can impact human health, of course, right? You pump out the water and you use it for your domestic purposes, drinking, bathing, and all of that. So it can obviously impact human health. It can also impact agriculture because that contaminated water is being used to cultivate all the crops, right? And if the water enters into the crops, right, then there is a process called bioaccumulation, right? So where the contaminant is present, it goes into the entire food chain, right? It enters into the irrigation water, and then some portion of that water may be taken up by the plants, right? So it's called plant uptake. The plant takes up that water along with the contaminant, and then that ends up in the seed or the fruit or whatever that's grown by the plant. And then when we consume it, so it's getting transferred not just through the water that we drink, but also through the food that we eat, right? So that's a major issue, right? Which means agricultural yield can also get impacted. If the water is contaminated, your crop may not give you, let's say, if you get 5 tons per hectare uh, using normal water, if you use contaminated water, you may only get 4 tons per hectare or something like that, right? I'm just giving you an example. So it can impact food security also, in addition to food quality, impacting food quality. And then there's the impact on the ecosystems. Now, animals and plants that also survive on water, they will also start dying because the water is no longer clean. It's contaminated with so many different contaminants, right? And a recent report from Niti Aayog actually said that more than 80% of India's water is contaminated: surface water, groundwater, everything, right? So that is the scale of the problem. That is the challenge that we are facing with the extent of the problem that we have. Okay, now fortunately, this problem is, we are not the first country to face these issues, right? These problems have been seen around the world, and people have made efforts to solve some of these problems around the world. Okay, so what I'm going to talk only about the experience from USA, because USA is a similarly large country, right? I mean, of course, it's 3 or 4 times larger than India, and they have also faced major groundwater contamination issues. But I mean, like in India, the industrialization started in the 1950s and so on, right? But in the USA, industrialization started even earlier, late 19th century, early 20th century, their industrialization started. So therefore, they started seeing these major groundwater contamination issues in the 1960s and 70s. Okay, and then there was a there was an act that was passed, which is called the Comprehensive Environmental Response Compensation and Liability Act, CERCLA, that was passed in 1980. Okay, and they have an agency similar to India's National Green Tribunal and so on, Minister of Environment and so on. They have the EPA, Environmental Protection Agency. And what they've done is that they've investigated and tried to clean up sites that are contaminated with hazardous substances. So they have a list of substances which are classified as hazardous, and any site that has been contaminated with these hazardous substances, they identified more than 10,000 sites across the US. Okay, these sites are called the Superfund sites. The Superfund that I've written on the title, the Superfund sites is basically those 10,000 sites which are distributed across the United States. Okay, and what they've done is that they said, once we identify a site that is contaminated, we try to find out who is the person who polluted this. When I say person, I mean it could be an industry or it could be an organization, whatever it is. Who is the polluter? Okay. So the principle is that the polluter has to pay. Whoever polluted the groundwater or the surface water, whatever it may be, mostly groundwater, but polluter pays principle. That is the principle. Whoever is the polluter, that person or that organization has to pay. Okay, so that is what is called the potentially responsible parties, right? So you identify who is the party that caused this pollution, and then you recover the money from them to in order to clean up these sites. Okay, now imagine the challenge of this 10,000 sites across a vast country. India will have similar kinds of numbers. Okay, we might have 50,000 sites or whatever it is. We might have even more contaminated sites. We don't know. Anyway, so therefore, there is a systematic methodology that they follow, right? Once they identify a contaminated site, they try to find out who was the person responsible for the pollution, and then they try to recover money from them. If not, if they don't have the money or if they are bankrupt or whatever it is, they have a procedure that they follow. Okay, we are not worried about that. Let us focus on the methods that can be used. Okay, now the cost estimates for cleaning up these Superfund sites, right? At present cost, it's around $2 billion per year. Okay, huge numbers. Okay, which is, of course, in India it translates around 16,000 crores. So per year you have to spend that kind of money to clean up these contaminated sites across the US. Okay, now in response to that, in the US there is what is called the environmental consulting industry. So lots of small companies started developing in the United States from the 1980s onwards, because once the market works like that. Once there is a need to solve something, there will be companies that come up which will help you try to solve it. Okay, so this environmental consulting industry developed in the US from the 1980s onwards. Okay, when the environmental regulations and all of those came into effect. Now, one of the major challenges with groundwater is because you can only see the contamination at a particular location. If you drill a well, you will see contaminant in the water. Okay, then you know that there is contamination present here. Okay, but let's say I start cleaning it up. How do I know when the contaminant is completely gone? I can't drill a well everywhere. I can't drill up the whole earth and I can't excavate the whole earth and then say and then try to clean it and put it back. It's not possible. It's not physically possible, right? So the problem is that the contaminant is invisible to us. we can only see it at particular points. I drill a well here. If I find contaminant, I know it's contaminated. If I drill a well somewhere else and I find there's no contamination there, you can say there's no contamination here at this point in time. But in future, that location may also get contaminated. So we don't know, right? So the challenge for us is as groundwater hydrologists is to come up with a method that is foolproof to the extent possible, and that can clean up the sites and say that now it's done, the cleanup is over. But the problem is that many sites, in spite of they started working in the 1980s and so on, they've been working on 10, 15, 20, 30, 40 years, and still many sites are still remain contaminated, or they've not been able to resolve it completely and say it's over, it's done. Okay, they've made progress, but the contaminant it just refuses to go away, right? Because it's so complicated, it's invisible and so on, right? So therefore, similar challenges exist for us as well, right? Of course, they started 40 years back or 50 years back, and still they have these issues. If we start today, it will take 30, 40 years to get to that stage where you can say it is cleaned up by 70% or 80%, but still some 20% is left or whatever it is, right? So it's a long drawn out process, and therefore it requires understanding of how to go about solving this problem. Okay. Okay. I'll just discuss a few potential ways in which this contamination can be cleaned up. Okay. There are many different ways, and this is just a brief list of maybe I have 5 or 6 different methods that can be used to clean up this kind of contamination. And these methods also vary from place to place, depending on the local conditions, depending on the type of contamination. You'll have to use a different method, right? So one of the methods is called in situ chemical oxidation or reduction. Okay, so basically what happens is the contaminant is present underground, and then I install a well where I pump in some kind of an oxidizing agent or a reducing agent, which will convert the contaminant into some harmless byproducts. It seems like a fairly obvious way of handling it. If there is a contaminant present, if I can convert it into something harmless, then that reduces the problem, right? So I inject some oxidizing agent or a reducing agent into the ground, and when that comes in contact with the contaminant, it reacts and produces something that is harmless byproduct, and then that thereby the problem is resolved. Of course, you will have to monitor the concentrations as a function of time. You have to watch that, okay, the concentration is starting to go down as the contaminant starts getting to reacting with the reacting and producing the harmless byproducts. You should observe a reduction in the concentration of the contaminant, and that could be an indication that the contamination is reducing as a function of time, right? So the typical types of oxidants that are used: permanganate, persulfate, hydrogen peroxide, ozone, all these have been used because they don't cause any other issues, right? And then similarly, if for reducing agents, you have zero valent ion, polysulfides, whatever, sodium dithionite, I don't even know what that is. Anyway, so there are all kinds of other methods that are other agents that are reducing agents that are used to try to um, remedy this type of contamination. Okay, now the advantage of this method is that it's relatively fast and it's cost effective. Okay, if I know that the contaminant is present over a relatively small area, I can use this method to very quickly and in a cost effective manner reduce the contamination, both in extent and in terms of the concentrations and so on. Okay, so that's one possible method. Another method that is used uh, to remove contamination is what is called the permeable reactive barrier. Okay, so now this picture explains it very clearly. Okay, so there's nothing more to explain, right? So there's some contamination that has entered into the ground, and it is flowing with the water in a particular direction. Then what we do is we build a barrier. Now, when I say barrier, it doesn't stop the water. It's a permeable barrier. Okay, so it's something that I build across the contaminant in the direction of flow, across the direction of flow. And what I do is, in that barrier, I put in some reactants which can again react with the contaminant that's present in the water, so that when the water leaves the barrier on the other side, it gets treated and then it just moves away. So the picture is explaining it pretty much. uh, whatever your whatever you need to understand is pretty much there in the figure itself, right? So I build a barrier across the direction of flow, and when the contaminated water moves past the barrier, it gets treated, and on the other side you just get clean water, right? uh, but the challenge with this is it may take many years to clean up the water, right? And you also have to make sure that the groundwater flow direction doesn't change, right? For any reason, whether for natural causes or because if the gradient changes, then the groundwater may start flowing in some other direction, then it may not flow through your barrier. So that is something that has to be taken into account, right? And then of course, this barrier that has been placed there, once it reacts and you know if you fill it in with some material that will react with the contaminant, you also have to replace that contaminant once it loses its efficiency and so on, right? So you fill in some material, after a certain point it's completely reacted, and therefore you can't it won't have any more efficiency, so you have to remove the used material and then replace fresh material in that, so that it will continue to act as a uh, uh, you know effective measure to remove your contamination. Okay, so you can think of, there might be so many challenges with this. How to know where to build this barrier? That's the first question that you may ask. In this figure, it's shown nicely that the contaminant is moving this way. I build a wall across that. How do you know where the contaminant is moving? So first of all, you need to collect a lot of data and try to understand what direction the contaminant is moving. Okay, so that becomes your uh, 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 first line of understanding, is to know where the contaminant is moving, in what direction it is moving. Only then I know where to construct this barrier, right? Because all of this is underground, it's invisible. So even to know where this contaminant is moving, you need to collect a lot of data. And then after you construct the barrier, it also becomes your responsibility to make sure that it doesn't move in any other direction. If it's moving towards the barrier, that's the best option. If it starts moving in other directions, you will have to control the maybe by pumping or something, and change the flow direction back towards this barrier so that the barrier is effective, right? You can't go and move the barrier, it's not possible, right? It's already embedded under the ground, right? So these are very challenging problems, right? Which requires basically, you guys to go out there and implement this, right? India has started cleaning up a few sites around the country. I think some 8 or 10 sites they have picked. And uh, I saw, if I find that news article, I'll share it with you guys. Some 8 or 10 sites have been picked around the country where they are going to start cleaning up groundwater sites, right? Contamination site. Okay, the numbers are very small, right? Because you need so much money, so much expertise. But at least we are starting. So hopefully more and more sites will get identified, and more of these sites will get cleaned up, which means more and more jobs, basically, right? Which is good news. Okay, anyway, moving on. Another popularly used method is called the soil vapor extraction method. Now, this particular method is suitable when the contaminant is some kind of a volatile organic compound, right, or petrochemicals, something like that, right? Basically, something that will evaporate. So what you do is, I know where the contaminant is present. I inject hot air into the ground. When this hot air comes in contact with the pollutant, it causes the pollutant to evaporate. And then when it evaporates, I have an extraction well that will just pull out those vapors, right? So it's called soil vapor extraction. The name itself is fairly indicative of what is going on. And again, fortunately, these figures, I have taken these figures from the EPA website. Okay, most of these figures are coming from the Environmental Protection Agency's website, and they do a great job of explaining exactly what is happening in the system, right? Very simple, nice illustration. Of course, the challenge that I already mentioned is you need to know where the contaminant is present. You can't just, you don't have an X-ray vision to look into the earth and say, hey, this is where the contaminant is present. So we have to collect a lot of data to find out what is the extent of contamination, and then decide on the appropriate course of action to remove that, remove the contaminant. Okay, of course, advantages, disadvantages, those are all there. Okay, anyway, if there are any questions, please stop, because I'm doing all the talking now, and you can just stop at any time and just ask me any questions. Okay, okay. The next method is called in situ thermal treatment. Okay, now it's very similar to the soil vapor extraction method. In this particular one, you 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 place some kinds of electrodes, right, which can actually heat up the soil in that particular region, right? So it will heat the contaminated soil or the groundwater to relatively high temperatures, and when that happens, in that high temperature, the contaminant may either vaporize or it may even get destroyed, right, depending on the nature of the contaminant. And then when it vaporizes, you may again extract out the the contaminant out, and then remove it. If it gets destroyed, that's best, right? If it vaporizes, then you extract the vapors, because it's in a different phase. It just escapes because it's lighter than water. It will start escaping up, right? Because it's any hot air will automatically start moving up because it's lighter. So when it moves up, we just use some kind of extraction system to remove the vapors, right? And depending on how much the contaminant is present, the concentration may be really high. If that is the case, then you just condense the vapors, and it might be some kind of useful chemical that can be reused again, and you continue using the system. Make sure that the contamination doesn't happen. Okay, I mean the material is disposed of in a safe manner. Okay, let's move on. One more. Now, this is a very popular, used to be a very popular way of treating contaminated groundwater, but it has become more and more less popular as time has gone on, because people have found many problems with this. The idea is pump and treat. Okay, if you find contaminated water, just install a pumping well there, extract the contaminated water, treat it, and then just dispose the water in some nearby river or something like that. Okay, or maybe inject it back into the ground, something like that. Now, the problem with this method, people observed, was that this treatment process has to be done to a very high standard, to a required standard, so that you can either reuse that water or dispose that water, right? If that is not done, then what you're doing is you're taking water out, treating it, but if not done properly, then you're disposing of dirty water in some other stream. So you're spreading the contamination. At least when it was underground, it's not visible, right? Now you're taking it out, you're not treating it properly, and then disposing it off. And also this pumping out untreated water is very expensive, right? Because you have to keep the pumps running for hours and hours and months and decades probably. So the cost of pumping out so much water is huge, right? So therefore people have tried to move away from this uh, uh, pumping out water, because the cost of pumping really becomes very expensive, right? Because it's not enough to just pump for a short duration. You have to maybe pump for decades, right? So the electricity cost, the pumping cost is basically very high, and then the pumps will also require replacement, and so on and so forth, right? So it's a very expensive method, but it was the first thing that was tried, was pump and treat, right? Because uh, whenever you think of something, if there's something contaminated, just remove it and then uh, uh, throw it out, right? That's the first idea that was tried basically. Okay, it has issues. All right, one more. Now this one is I wouldn't say it's a cleanup method. It is more of a containment method, right? Rather than allowing the contaminant to spread, you just try to maybe contain it by saying, let us build a impervious barrier to this contaminant, so that it doesn't spread beyond a certain region, right? So again, in this figure you can see very clearly, instead of allowing it to spread further, you just construct a wall all around the contaminant such that it may not spread further and go and contaminate the whole aquifer in all directions. Right, so you'll have to come up with what is called a vertical engineered barrier, VEB. Right, so sheet piles, slurry walls, all of these different methods are used to contain the contaminant basically, and then if you want to use the water inside this contaminated region, contaminated area, then you'll have to, of course, treat it so that it uh, uh, doesn't cause any issues as such, right? So this is another um, you know, another potential method for cleaning up this kind of groundwater contamination. Okay, we are almost towards the end. So now, whenever it comes to um, cleaning up this groundwater contamination, there are some major processes that you have to follow in a project in order to uh, be able to successfully treat it. The first thing, the first step on the left, I've written this. Now, this step is so important that I cannot stress it enough. Site characterization. Once I know that a particular site is contaminated, although that word seems very simple, site characterization, it's got so much has to go into that, right? What it means is to first try to understand what is the contaminant that is present, at what concentrations is it present, over what area has the contaminant spread currently. Okay, so just to understand all of this, you will have to collect a lot of information around the site, right? It's not enough to just collect it there. If you notice that a site is contaminated over a certain area, you have to sample around the site to find out in what direction is it moving. Is it moving? At what rate is it moving? Right? How long has it been contaminated? So you're trying to gather all the information possible to characterize what is happening at that site. And then you come up with an idea. So for example, if you go back to this, uh, let's take a look at this figure, right? This white area that's shaded, that is the extent of pollution. How do you know that is the extent of pollution? You can only know that if you have sampled a lot of data around the site to ensure that I know that only this region is polluted. There is no point in spending your money trying to clean up a place where there is no contamination, right? So it becomes very important to know what is the extent of the contamination and then try to clean up only that portion of the aquifer, right? Because it's very expensive. You can't go around trying to clean up a place where there is not much contamination, right? So you have to come up with a conceptual model, conceptual site model, and then you design the treatment according to the type of contaminant, right? If it's a volatile material, then you may opt for something where you apply some heat to extract the vapors and so on. If it's some other type of contaminant, you might have to come up with different methods, right? And then you implement. So up to this point, you've not started doing anything. This first three steps itself takes a lot of time and a lot of effort, a lot of money to understand the site, to understand or to come up with a conceptual model of how to treat it, and then depending on the nature of the contaminant, what kind of treatment approaches have to be used. Once all of that is done, then you start into the implementation and the optimization of the actual treatment itself. And even after that, it's still not enough. You have to monitor over time to make sure that whatever you have done is working properly, that the contaminant is not escaping away from there and going and contaminating more regions around the site, right? So there has to be some kind of a long-term monitoring approach to ensure that, number one, whatever you think you are doing, you are actually doing it, because you can't see it physically. You have to depend on monitoring wells that are present around that contaminated site to collect data to let us know whether the approach that we're using is working, to what extent it is working, whether we need to do anything, make any improvements, and so on and so forth. So it's an iterative process, right? So these are some of the major steps that are involved in cleaning up a site once it is contaminated. Now, what I would like to stress is, fortunately, other countries have done this before. Okay, they have made mistakes and they have learned their lessons and they have come forward. Now we are joining this game late. Okay, of course, fortunately, industrialization did not start in India I mean, that much in the past. It only started in the 50s and 60s and so on. So the contamination is also recent for us. Okay, it has not been happening for so many years. It has only started in the 50s and 60s majorly. So relatively speaking, it's also new. The problem is newer for us, but we don't have to make the same mistakes that all the other countries have made and then arrive at the right solution. We can learn from them and directly arrive at the right solution, right? So this is something that I always say. In some of the older, the more industrialized countries, they go through all the stages of development. They went through a landline, then they did a cordless phone, and then they came to a mobile phone, and then they came to smartphone. Whereas most of our Indian people, we never had a landline phone and this phone, that phone. Directly we arrived at smartphone. The first phone we purchased was a smartphone, right? That is the thing. So we don't have to go through all the stages and then arrive at the smartphone. We can directly come to the smartphone, right? Or maybe the kids who come up in the next 10, 15, 20 years, they might directly arrive at the whatever the newest technology. We don't have to go through every single stage to come to the final stage, right? So that's one advantage of what learning from others, right? You don't have to make the same mistakes, or you don't have to go through every step that they did, right? But in any case, so basically what I'm trying to stress is that there is a lot of scope to try to resolve these issues, and there are lots of organizations that are working on trying to resolve these problems. Now, if you go to Bangalore, for example, they have a major water contamination problem in the lakes around the city, right? So there's an organization which is trying to clean up the lakes around the city. There are organizations like that in Chennai. There are organizations like that in Delhi, now with the Yamuna and all of that. So um, it's up to you to be able to use all this information, whatever we have learned here. Some of these ideas you can take. I mean, I'm just given a brief set of 5 or 6 treatment options. There are other options available, right? So you can look those up and then try to learn about it, and then hopefully you get a chance to do something about cleaning up these problems and so on and so forth. Okay, so I'll stop with that. We will meet on Tuesday next week, and we'll start the final chapter where we'll discuss a little bit about groundwater modeling, right? That will be the final chapter that we will discuss. And yep, so see you guys next week on Tuesday at 10 a.m. Okay, all right, thank you very much. Take care and see you all on Tuesday.